Okay, thanks everybody for coming, whatever the reason. So as he mentioned, I work now on energetic particle observations, so it's a little bit different than the aurora, but I was really excited to be asked to give this talk because one of my first loves in space physics was the aurora, and I did my entire graduate career on that. So it's really nice to be able to go back and show some of those observations, even though I don't currently work on that so much anymore. So tonight I'm going to talk about the origins and the mystery of the aurora. And basically I'm going to tell you everything you ever wanted to know about the aurora. We'll go through the history of the aurora, some recorded observations, foundations of auroral science, what exactly is the aurora, where do all the pretty lights come from, the types and features of auroral forms, why do we as scientists care so much about the aurora. We'll look at observing and studying aurora and how you do that from ground-based instruments versus from space, and then from in between, which constitutes the sounding rocket program that I'll talk about. And then I'll show you some pictures, what it's like to be a rocket scientist in the field. And then at the end, I'm going to talk about getting a little more involved. So if you want to be interested in the aurora in terms of citizen science, and then also if you are interested in looking at ways to predict space weather, and if you can see aurora from, say, Boulder at a certain time, and then tips for observing aurora yourself. So the historical record dates back to about 2600 BC in China. That was the first earliest recorded observation of aurora. Possibly could have been something else, but it's probably aurora. There are some cave paintings from earlier, but they don't really convince me. It's sort of just like a serpent in the sky. May have been aurora. We have definitive records from 700 BC in China that are definitely discussing the auroral lights in the sky. And then if we skip forward to 5th century BC through 10th century AD, people started writing down stuff a lot more, and we get various references in Roman, Russian, and English records. And then in 1192, we have records of this great aurora observed by many throughout the world. So it's kind of cool. It was this global event that a lot of people recorded, a lot of people experienced. They couldn't really, it's interesting to think about because they couldn't really talk about it like we do today across countries and cultures. But a lot of people saw that at once, and it was recorded in many places. In the early 1700s, we had multiple accounts of intense aurora from China, New England, and Europe. And then in 1859, that might strike a bell with you because that was the Carrington solar flare event that was recorded by Carrington. And in the days following, there was the brightest auroral event that has been accurately recorded and ever written down to date. In fact, aurora was observed all the way in South America, intense aurora. And so we probably hadn't seen anything like that. We haven't seen anything like that since, and it was unlikely that it was seen before that. I put this etching here from 1570 AD because this is kind of what people thought originally, was that, you know, there's this birthday cake in the sky with these candles dancing around, but they just really didn't know what to think. You know, they didn't know that this was electrical currents. They didn't know these were electrons and protons flowing in from the sun and eventually getting trapped in the Earth's magnetosphere and then forming the aurora. And then I also have this quote from Pliny the Elder, which I really like. He described the aurora as a flame of bloody appearance, which falls down upon the Earth. And this was actually thought about this way by a lot of cultures. They equated this with war and with something maybe terrible about to happen. And then, you know, eventually it was realized that these things happen periodically. There's nothing to be scared of, and they don't mean anything terrible is going to happen. So early researchers were mainly concentrated in Norway, and that was because they were, you know, they were pretty adventurous. They liked to go on expeditions, but they were also living in the right place, so they could see aurora much of the time in the winter when it was dark. So Kristian Birkeland was one of those early auroral researchers. We owe a lot to him in our thinking of the aurora to this day. He was the first one that really connected the northern lights to being electric currents, and to those electric currents being formed by particles streaming from the sun. And then he has this whole really deep quote about how, we think of space as being filled with matter, but it's really just this sort of empty space in between everything. And these are the kind of deep thoughts you have when you're sitting in the Arctic watching an aurora night after night. But he was really quite forward thinking in that, because it turned out to be, very much what turned out to be the case, is that we see there's a lot of mostly empty space, and that's where the mass is in the universe. So that was really cool that he came up with that. He set up observing stations, he organized expeditions, he performed laboratory experiments, as shown here, where he was trying to sort of simulate aurora in the lab. Then Carl Stormer, another Norwegian, he took hundreds of pictures on expeditions. He went to the Arctic, he went to the places where people hadn't brought film equipment before. He made extensive notes and observations during those times, and he even formed the basis for classification of aurora that we still use today. So what causes the aurora? Well, it's pretty much a process very much like a neon light or like a neon sign. So you have particles streaming in from a certain process, which I'll talk about in a minute, and they collide with the atmosphere at altitudes depending on their energy. And when they collide with particles or with molecules or atoms, they can either excite those molecules and atoms, or they could break the molecules apart. And when they do that, they release photons. And you can have cascades of photons occurring from just one incoming electron. So you can think of this as a shower happening, one effect after another, all the way down through to the lower atmosphere. And the important thing here is that photons are given off in certain specific energies, in quantized bits of energy. And so when you have these collisions taking place, instead of getting a full spectrum like you see in visible light from the sun over this entire swath, you get these very discrete emissions occurring in the aurora at certain colors, and that depends on the wavelength of which the energy that they give to the particle, and that then lets it out as a photon is receiving, and that has to do with quantum mechanics. And so we can use the spectrum of the aurora to sort of study what molecules are being affected by these incoming electrons, and we can also start to make some assumptions about what chemistry is going on between those incoming electrons and the atmospheric constituents. And I wanted to show this figure from aurorasaurus.org, a website I'll talk about later, that kind of shows the altitude profiles and where you get the different colors. You can have primary collisions. You can also have secondary electrons being emitted, and then those can collide with other things, and you get secondary emissions. So it's a very complicated chemical process that happens. And I want to point out this point on the bottom here is that most aurora is not caused by solar wind particles directly coming from the sun and hitting the magnetosphere and then showing up on Earth. And so this is a point that a lot of even physicists misunderstand, and they can get that wrong. So that's something I wanted to sort of let you guys take away from this tonight. So what does cause those particles to enter our magnetosphere? Well, it does originate on the sun. So you have things that can be ejected from the sun. You have things like CMEs or larger flows of plasma coming from co-rotating interaction regions. And they do, and then that kind of plasma does impinge upon the magnetosphere. But what it does is it starts to increase this convection and strip away these magnetic field lines around the Earth's magnetosphere. And then that puts pressure on the tail part of the magnetosphere, which squeezes it, which thins the plasma sheet, and then you can have an explosive process happen in the tail called magnetic reconnection. And then what happens is these particles get accelerated, they stream down the field lines, they hit the atmosphere, and they become aurora. So it's not really particles that are coming straight from the sun and then dumping into the magnetosphere, but it's more of an energy transfer. So that stuff that comes from the sun puts energy into the magnetosphere, and then that eventually accelerates electrons that are kind of already within the Earth's magnetosphere. So another important component of this is the particle motion in the magnetosphere. You've probably seen this picture before, or many of you have. It's a schematic of the Earth's magnetosphere. We have a compressed magnetic field on the part that's pointing towards the sun, and we have this extended magnetic field away from the sun that gets blown by the solar wind and sort of forms this windsock pattern. Particles in the magnetosphere also undergo a bounce sort of motion. They undergo several types of motion, but one of the important ones for this process is the bouncing. And so what happens is, based on their pitch angle, if they have a larger pitch angle or the angle between the velocity vector and the local magnetic field, if that's larger, they won't bounce as far. So they won't travel as far before hitting their mirror point and turning around and coming back. If they have smaller and smaller pitch angles, they will go deeper and deeper down this magnetic field line. And if that pitch angle is small enough, they will eventually make it very far down, very close to Earth, and they will likely collide with the atmosphere. And then that's when you get those auroral particles that I was showing in the previous slide. So there's lots of things going on that conspire to create this natural light show. So where does the aurora occur? Well, you've probably heard the term auroral oval, and so that's where the aurora occurs, in the auroral oval. But the auroral oval changes shape. It changes where it exists on the projection of the Earth. There's an oval in the northern hemisphere and one in the southern hemisphere. But we get, during enhanced geomagnetic activity, we get an expansion of this oval. And so it can grow, and it can sort of drift to lower and lower latitudes. And so that's the connection between when you have enhanced geomagnetic activity, you have changes in the Earth's magnetic field, and then you get an expanded auroral oval. And it might even dip down to this lower 48 status region there, which is probably the time that you would start to get interested. And that's all based on solar wind forcing and what kind of inputs go into that system. So I'm going to talk a little bit about auroral forms. I get to look at a lot of aurora, or I did when I was a graduate student, and so most of these pictures are pictures that I've taken or colleagues of mine have taken. So discrete aurora is basically the beautiful, pretty, explosive aurora that everyone likes to see. It's usually structured in these bands or arcs, they're called. You hear things like rays, which are these long structures or striations. You hear things like curtains, because they kind of look like it's a curtain waving through the sky. They can be east-west elongated or north-south elongated. You also hear things like draperies and corona. And I'm going to show some examples of coronal aurora, because it's just gorgeous. So coronal aurora is when you're looking up along the local magnetic field line and the aurora is directly above you. And you get this sort of perspective effect, as if you're standing in a city looking straight up at tall skyscrapers, and they look like they're converging over top of you. And so that's the same thing that's happening here. And imagine this moving as it would in real time, and just sort of whipping around and dancing overhead, and it's just the most beautiful sight that you can really imagine. And so coronal aurora is one of my favorite types of aurora. And so it's really nice if you get to see this. You have to be pretty far north, or you have to have that auroral oval to extend pretty far south to be able to see this type of aurora. So there's also diffuse aurora, which some people think is a little more boring, but I really like studying this type of aurora. It usually ends up looking like a faint glow in the sky. I've got a couple of pictures here. Some people even mistake it for clouds. It looks like a smear across the sky. Sometimes when I'd come back from rocket campaigns, I'd look up at home and see a cloud and think I was seeing aurora for a second, and then realizing, no, I'm back home, I'm not seeing aurora. So it can be a little tricky to study just visually with your eye, but there's some really interesting source regions for this type of aurora. And one of my very favorite types is pulsating aurora, which is explained in this fantastic article by Thomas Mallon, The Last Rocket Club, to be great patches of white on the screen, on the all-sky screen, that prove on closer inspection to be thin, luminous gruel, which is not really a very attractive description. But I'm going to show a movie of pulsating aurora that was taken on one of our campaigns, hopefully. And so this is sped up. This is not real time, but still you get to see the dynamics that are at play here. So these are large patches of aurora that are turning on and off. This is much faster. This is sped up. So these are actually oscillating at periods of seconds. But they're large patches that are lighting up and then turning off again. They're fairly irregular. They can change shape. They can drift and move throughout the event. So this is one of the things I've studied in detail in my career so far. I really like pulsating aurora. It tells us a lot about what's going on in the magnetosphere, and I just think it's fascinating. But it's not all that much fun to look at. Thin, luminous gruel in the sky. So other auroral forms that you also can find are, one example is black aurora. So this is essentially the absence of aurora, but it can be very striking. It can have very well-defined boundaries. Here's a still image of a couple of bands of black aurora that are embedded in a sky of diffuse aurora. And so this has been somewhat of a mystery because people will explain it as being sort of the anti-aurora. So you have a current going in the other direction, you have current closure through here. So if you have electrons going down, you have electrons going up over here, and you see this little thing of black aurora. But why does it keep such a sharp boundary? Why doesn't it get smeared out? And why does it sometimes move the way that it does? These are still very much unanswered questions. So that's a particularly fascinating type of aurora, but you don't see it very often, and it typically happens late at night, and it's faint. Curls and vortices are really interesting to study. Those essentially arise out of sort of twisted magnetic field lines, and so when things start to get really active, those magnetic fields can start to twist, and then you see that in the ionosphere, and the result is these curls that look really dramatic in the sky in the aurora. And then I also have some footage that I took on one of our campaigns of flickering aurora. Flickering, this is happening in real time. So flickering is a very, very high time fluctuation aurora. You can see it'll brighten up in a minute, but you can see it sort of looks like a flickering TV screen a little bit. And this is pretty interesting because something is happening on such a high time scale as to be reflected in this type of aurora, and we're still not sure what that is. It's probably something having to do with wave-particle dynamics that can also exhibit time scales like that, but it's also a really fascinating type of aurora that you don't see all that often, and I was pretty lucky to get that footage that was up in the north slope of Alaska. So I wanted to talk a little bit about phases of a substorm, because a substorm is essentially the release of magnetic energy that gets manifest into that aurora that you see in a auroral breakup sort of display. So you can see indications of this from the ground in the optical data, and you can also see indications in the magnetosphere. So I'm going to talk about each phase and what you would see. In the growth phase, from the ground, you see an arc form, sometimes overhead, sometimes to your north. It starts to move equatorward or south. So if you're looking up, it'll just sort of start to move over you and go south. You might see another one form and go south. And this might happen repeatedly. And this is during the phase in which the magnetosphere is starting to store energy in this tail. So you're getting that enhanced convection. These field lines are starting to squeeze in back here. This plasma sheet's starting to thin out. And this whole thing is gaining energy. It's like you're stretching a rubber band, and there's just a lot of energy waiting to be released there. The expansion phase is the exciting part. You see a rapid brightening of the arc. You start to see it rush northward, and then before it gets all the way north, it just breaks up across the sky. It turns into this substorm breakup, we call it. There's dancing lights everywhere. They're swirling and whipping around, and it's very, very dynamic spatially and temporally. And then what happens in the magnetosphere at this point is that this bulk of plasma has just been created from a magnetic reconnection sort of explosive event that I had shown in that movie. And so what happens is some of that bulk plasma rushes towards Earth. It kind of gets ejected. The other part of it ejects down the tail and just leaves the magnetosphere. But the part that comes towards the Earth, these accelerated electrons will stream in, they'll hit the polar regions or the auroral oval regions, and they'll become this fantastic aurora show. So you can see here there's a little bit of a sequence of images showing the oval is very nice and quiet. You can't see it so well on this scale, but this turns into a substorm. And then of course if you were to watch this move, it would just start to go crazy and chaotic. And then eventually you get to the recovery phase, which is when all the energy has been released. There's these leftover patches kind of floating around in the sky. It's sort of that thin, luminous gruel appearance. Later on, those little patches will start to join up and form into larger patches, and those will start to pulsate typically, and you get pulsating aurora into the dawn sector. But you can also have another substorm start. These things can happen on the time scale of an hour. So an hour or so later, you can have the whole thing start over again. And so they're really cool to watch, just repeated events of those over and over. So what's the importance of studying aurora? Well, one of the main things is that we get a window into space weather and magnetospheric science, kind of like what I just showed. We're looking at a view of that from the ground or from a rocket, and we're seeing things that are happening in the larger system, but we're looking at them in this sort of nice, finely detailed way. So it gives us a really nice look into those processes. We're also getting this natural plasma physics laboratory in our backyard. So we can just wait for the aurora to happen and then shoot a rocket into it, which is really nice. We don't have to recreate plasma in the lab. We don't have to do any fancy experiments. We just get a rocket ready and we wait. So this was a picture from one of our sounding rocket campaigns in which we had a very successful launch in 2012. And the third reason, I think, is that there's some fundamental processes that we still don't understand. So there's a lot of mystery surrounding these plasma physics processes. This is actually a figure from a real paper, a peer-reviewed paper, in which the authors decided to place the sea monster here in this, to mark this region of unknown. And this is sort of the top of an arc. Where do the currents close? We still don't know. This was published in 2001, and it's being depicted as a sea monster, right? So there's a lot of things we still need to understand, and I think this is a perfect way to do that, is to study the aurora. So one of the ways we look at the aurora and we do science with the aurora is using ground-based observations. So here I'm showing an array of imagers that we use very commonly. This is the Themis ground-based network. It's co-funded by NASA and Canadian Space Agency. It's a chain of all-sky imagers across that Canadian and North American extent. It goes all the way from Alaska to eastern Canada. They take 3-second integration images of white light. So you get really nice all-sky views of the aurora in 3-second steps. And this is sort of looking horizon to horizon, almost 180 degrees. It's a little bit like a fisheye point of view because you get some distortion at the edges, more so than in the center. But you do get this really nice horizon to horizon view. And so you can look at these things. I'll show a movie in a second. You can look at aurora that happens across all of these local times simultaneously. You can use them with spacecraft that are flying over and do conjunction studies. So this is a really powerful tool that we've used quite often in our field. So this was a study I was involved in that we published in 2013. And I'm going to show this network of all-sky imagers. All of this flickering, this is sped up greater than real time, but all of this flickering is pulsating aurora, so that those pulsating patches I showed earlier. But the big point here is that it's happening across North America, a huge geographic extent, huge extent in local time, and it actually lasted for over 20 hours. It was this enormous event that's not very unique. So our point here was to show how often pulsating aurora happens, how widespread it can be, and how persistent, how it can last for hours and hours. So this was a really cool way to use that entire chain of imagers. So ground-based observation in 3 words, or pictures rather. It's very economical. So here I'm showing an imager we had in our field station in Toolik Lake in Alaska. It's basically just a plywood box with a plastic dome on top. It's very cheap. The most expensive thing is the camera. It's a very economical way to do science. It's also very cold, so if you want to observe aurora and you want to observe it often, you have to go to Arctic and Antarctic regions. This is one of our remote stations in Antarctica. I was sent down there to retrieve some data and basically dig it out of the snow on one field expedition. And it's also full of adventure. So if you're looking for adventure in your life, you should definitely think about studying the aurora, because you get sent to crazy places and you get to do all kinds of cool things, meet wonderful people. So there's also a space-based component to observing the aurora. And I'm going to start this section off with showing a movie from the International Space Station. This is actually a series of images that are strung together to create a movie. And so it's looking at auroras, it's flying over. This was in September 2011. You see really nice arcs. You see this really tall vertical extent of these rays coming up. It's just beautiful. You also see pulsating aurora. I don't know if you noticed it when it went by. I'm going to play this again because that was one of my favorite things about this movie, was that not only do you see that bright, nice discrete aurora, these arcs up here, but if you look in this corner coming up, you'll see these large patches that are turning on and off, and that's pulsating aurora. So it may not be the first thing that catches your eye, but it's really cool to see that happening all at once. This was just a great little movie that they made. So from space, we use a lot of different platforms. We've had a multitude of missions that have looked either in part or in whole at the substorm problem. We've had Themis, FAST, Cluster, also Swarm, Van Allen probes, and MMS. While they're not directly looking at substorms, they are looking at magnetospheric processes that result in substorms. We also have used coordinated ground and space-based measurements. And if you'll notice, LASP plays a major role in pretty much almost all of these missions here, so that's really cool. Some of the big science things that we've found out through these missions have been that tail reconnection causes substorms. So that movie I showed where that little explosive reconnection event happened, that's something we found out using these types of satellites, Themis in particular. We've also measured current structures in the aurora. We've shown that substorms can be made of these repeated dipolarization fronts that come flowing in very narrow channels we call bursty bulk flows. So it doesn't always have to be this global picture of a substorm, but it can be really tiny events kind of piling up and happening one after another. We've seen twisting of flux tubes that create those curls and vortices during substorm onset. We've looked at the cause of black aurora, and we've also looked a lot at the source of pulsating aurora and have seen that it's come from wave-particle interactions in the equatorial magnetosphere that are then modulated at a certain frequency so that you see the on-off pattern in the ionosphere. So that's all been really exciting science that has come out of the space-based components. There's still many outstanding questions, though. So one of the most debated questions is the substorm model. Is it an inside-out or an outside-in sort of event? So you can see here the two different types. Either you have something disrupting the current very near to Earth, then you see aurora, then you have reconnection, or, which is probably more likely or more often to happen, is you have reconnection down tail, then it causes current disruption, and then you see the aurora in the polar regions. So there's been a lot of debate, though. I've seen grown men stand up in conferences and scream at each other about these two models. And you can look over years and years of data, and there's billions of dollars that have been poured into this question, and you can still find very perfect examples in the data of each one of these. So clearly they both happen. I think it's a matter of how often or which sort of conditions set up each type of event. But the bottom line here is that we kind of need to keep funding auroral missions, and we need to keep studying this because there's so many unanswered questions, and they're all just fascinating. So I wanted to talk about one study that I worked on this past year, which was a coordination between space and ground, and that's something that really hasn't been worked on that much and not that closely, but I think it should be. I think there should be more emphasis on coordinating what we see either on the ground or using ground-based measurements and seeing what's happening in the ionosphere versus what's happening further out in the magnetosphere, and so down along those field lines to the equatorial region where those field lines start to turn around. So this is some ground-based all-sky data of pulsating aurora. And then I'm looking also at wave data on Van Allen probes out in the magnetosphere. There's actually a correlation between the two, so I won't go into it in detail, but this was just a really nice way that we were able to use ground optical data and space-based wave measurements of plasma waves and connect the two and show that something was happening, something similar in both places that were probably very likely related. So I'm going to talk a little bit about rocket-based observation. First of all, what is a sounding rocket? Well, this is a suborbital research vehicle. We put scientific instruments on the payload, and we then shoot it into space and let it crash. It usually crashes in the Arctic somewhere or in the ocean, and we don't recover it. Although lately, NASA's been trying to get have more of a green image, and they have been sort of putting rewards out for people in these areas to go out and find pieces of the payload, recover them, bring them back on their snowmobiles, and NASA will actually give them a monetary reward, which is kind of interesting. But typically, historically, they've just been ditched in the Arctic. So where do sounding rockets fly? They fly in this really nice region between where a balloon can exist and the lowest orbit that a satellite can reach, or had been able to reach until very recently. So sounding rockets kind of extend through this auroral precipitation region, so it's great for studying aurora. The sounding rocket program in general is fantastic. It provides training for students and young scientists. So the entire life cycle of a sounding rocket mission is about 3 years. From the time it gets funded, as a graduate student, you can work on a proposal, you could see it get funded, you could then go on the integration and testing part of the mission, you can then go into the field and launch the rocket and do the science all in like a period of 4.5 or 5 years in a graduate student career. So it's really nice for that. You get to work directly on instrumentation. Usually for satellites, you don't get to work on the instrumentation directly. So there's moderate risk involved in the rocket program, but that also means that you get more hands-on, and that you get to do a lot of crazy ideas that might not fly if you're doing a satellite proposal. You could say, let's try and do this crazy idea, and they might just take it because it's a sounding rocket and it's less money, and there's higher risk involved inherently. So it also, like I said, traverses a region of space that's extremely hard to observe in situ unless you are using a sounding rocket. The downside is that you only get about 10 or 15, maybe 20 minutes of observing time in that region, because the rocket just goes straight up and then it turns over and falls straight back down. And so you have a very limited amount of time that you can sense that region, but it's very valuable data. You can't get it any other way. Travel opportunities abound. Who says space physicists can't be field scientists? I actually did have one professor say that to me, but he was a theorist. So it's the most fun, rewarding, and nail-biting research that I've ever been a part of. I highly recommend it. So a little bit more about the rockets that we use. This is sort of the scope of the rockets. They range from very small to very big. You can get single stage all the way up to 3-stage rockets. And the payload is really just this tiny portion at the top of these rockets, and the rest of it's all motor to get it up in that altitude. And these are mainly military surplus rockets, which make for very interesting situations in which things have been sitting around since like Cold War era, and then they take them out of storage and try and fire them into the atmosphere. And so things can go wrong. So here I'm showing a picture I took at one of our rocket mission integration and testing campaigns. And this is actually the payload of a Black Brant 12. So this part kind of gives you a scale. This part is just the payload, not the motors, portion of that Black Brant 12. So they can be big, but they're not huge. They're not like the same kinds of rockets that we use to launch orbital vehicles. So you basically launch from 2 different locations if you want to study the aurora. You launch from Poker Flat in Alaska, or you launch from Andøya Rocket Range in Andenes, Norway. At Poker Flat, you're sort of in the middle of Alaska. You're a little bit north of Fairbanks, but we do have field sites downrange at Fort Yukon, at Toolik Lake, which isn't on this map, and then at Kaktovik. Kaktovik is where I've spent many, many weeks. So it's way up here on the north slope of Alaska. And what you do there is you basically observe. You look at the sky, you take optical data, because the rocket's going to fly out of Poker Flat and directly overhead at Kaktovik, or at Fort Yukon, depending on which trajectory and which altitude you go to. But essentially, you want someone there on the ground, gathering that data, watching the aurora, looking for the right conditions, and then alerting the launch team down in Poker if they should get ready to launch or not. Mainly involves many, many nights of just sitting there doing almost nothing except staring at the sky and wishing for the aurora to appear. But it can be quite fun. So in Andenes, you have the same situation. You launch from this northern coast of Norway, and it goes over this island here called Svalbard, and then crashes somewhere north of that. So I've also spent a lot of time downrange at this island here. It's very, very close to the North Pole. There's absolutely no sunlight there in the winter at all. So one of the interesting stories that I always heard as a graduate student, because my advisor was involved with this, was when one of the NASA sounding rockets got launched in an abnormal trajectory. It went very outside of its nominal trajectory. It started to go straight up and then kind of just flipped over and headed towards the Russian continent. And apparently there was, as you might imagine, it surprised them. They, of course, were monitoring the airspace, and they went so far as to get the nuclear codes. There was mention of a nuclear briefcase, and all that. So it was this big scare. It didn't really come into the media until weeks later because they didn't want to alarm anyone. But after that, a lot of protocols were put into place and better communication between the sounding rocket program and whatever was going to launch out of Norway and the Russian government. So that was an unintended risk, for sure. So here's some, I'm going to go through some pictures that I've taken on some of my various field campaigns. Here is just what the payload of one of our rockets looks like without the skin on. You have all kinds of different experiments and instruments. Yes, this is aluminum foil. You kind of have just things sticking out everywhere. This is where we bolt everything onto the rocket. We hook it up. We put power through all of this. We hook it up to ground station emulators, and we sort of make sure that all of our instruments are working, they're working together. We then also put this on vibration tables. We do thermal testing. We just want to make sure that once we fly this thing into space, all of our instruments are gonna work as expected. Here's some of my colleagues and two of my fellow graduate students back here on one of the mission campaigns. And so, yes, we actually do stare at screens and watch little dot matrix printers print out data, and it's all rather ridiculous, but that's how the program is run. It's very much, they've been doing this for decades and really haven't changed much. But it's very robust, it works. So this is from, this is sort of what life looks like in Kaktovik. This was that northern part of Alaska that I spent many weeks at. This was during a period of sunlight, although we didn't have very many hours of that during each day. This is where we worked at night, this little tiny building here. It's a balloon launch facility that we co-opt and take over and put optics in here. There's a dome up top. We come out in this balcony and we set up little cameras that point towards the aurora. And then we basically sit inside this closet-sized room all night, hoping for a launch. And then we go back home in the morning. So this is, of course, at night. So you're awake all night doing this. And then in the morning, you drive back to your home. It's very cozy. This is actually an early warning station. And so what's in this dome here is radar equipment. And this is basically a military base that monitors the airspace towards Russia. So again, it's a holdover from the Cold War type era, but there's a couple of guys that live here full time and basically look towards Russia to make sure nothing's coming. That's what they do. So this is life in the Norway downrange field site. This is Svalbard. The town is called Longyearbyen. This long winding road is the road that you have to take, and then you come up this very steep mountain to get to the ice cat radar, and the KHO observatory, which you spend all night every night, is actually further up the mountain than this. It's very beautiful. If you can see it, I never saw it like this. This is someone else's picture. When I was there, it was dark 24 hours a day, and really makes you gracious when you take that first flight back to the mainland and you see the sun for the first time. You realize why people worship the sun for so many, thousands of years, because it's just something you start to miss after weeks of complete darkness. But so you take a car halfway up this road, and then all the scientists jump into the back of this belt wagon or track vehicle. There's my advisor, there's one of our colleagues, and then our Norwegian scientist jumps in the driver's seat and drives you up in this track vehicle the rest of the way to the top of the mountain where the observatory is and where all of our equipment is. And that's what we do every single night. And then in the morning we drive back down into town. This literally happens when there's a polar bear that comes into town and starts to threaten the citizens. The mayor of Longyearbyen actually jumps in a helicopter with his rifle, and they fly around, and he kind of doesn't shoot the polar bear, but shoots towards it and chases it out of town. So very different sort of society. But it's really fascinating. The people there are awesome. The lifestyle there is totally different than anything you've ever experienced, but it's just wonderful. So I really enjoyed my time there.
I have a question.
Yes.
So you said you go out at night when it was 24 hours dark. You aren't around the clock. You actually go out when hypothetical dark time.
Right. So even though it's dark all the time, it depends on the type of aurora you want to see. But usually the type of aurora we're looking for happens around local midnight. So even though it's dark in the day, dark in the morning, it can get a little bit light, sort of like almost twilight during the very peak hours of noon. But the aurora that we want to see happens around midnight, so we still end up going out in the middle of the night and working that sort of graveyard shift. So yeah, I just wanted to throw up a couple pictures of the perks of the job, because it's not all 24-hour darkness and all that. So you get to see this really beautiful geography, scenery everywhere we go. It just looks like this pristine natural environment. This is a picture I took on one of our rocket campaigns of the Aurora. Of course, you get to see that gorgeous aurora night after night. And then you get to see wildlife. So one of my favorite experiences was in Antarctica, getting really close to emperor penguins. And they didn't really seem to mind, so it was cool. I got to take a lot of pictures of them. So I wanted to end this talk with a section about observing aurora and how you can maybe get a little more involved in looking at aurora if you happen to go to these polar regions, or if it happens to come down to Boulder at some point. So one of the sites I'm involved with is an NSF-funded project called aurorasaurus.org. And this is a citizen science portal that was set up by a colleague of mine. I'm actually the representative scientist for the state of Colorado. There's a couple of us sprinkled throughout the United States and Canada. But you can basically sign up here to receive notifications. And the way that this works is if someone cites aurora in your area and tweets about it, it will be registered with this citizen science project. And they fine-tune the algorithms, so they try and get real auroral sightings versus if someone's talking about going to Aurora, Colorado for the night, or something like that. And you can actually help with that by verifying tweets. So you can go on there and say, yes, this is real aurora, no, this is not aurora. And that helps fine-tune the algorithm. But this is a really cool project. It just started a couple years ago. It just really got going recently. So I think it probably has a lot of potential. You can also see real-time tweets. So if you hear that there's a storm going on, you hear there's enhanced geomagnetic activity and you want to go check, you can look here and see if there's any tweets showing up in Wyoming or Montana, maybe even Colorado, and saying that they see the aurora right now. You also get this projection of the auroral oval onto the map and the probability of looking at a visible aurora from your region. Another cool feature is that sometimes we have these online chats where people will jump on and ask us questions and we can respond in real time and talk to real scientists, so that's kind of cool as well. So if you're interested in digging more into this and how, learning about how we predict aurora and what kind of tools that we use to do this, this is basically the setup that we go through when we go on these rocket campaigns to try and figure out what days are going to be most optimal for our launch window. I mean, we have to decide the launch window many months in advance, but once we're there, we can think, okay, maybe in the next few days we have a really good opportunity to launch into a certain type of aurora. So how much lead time do we actually have? If you use something called a condygram, and this is named after Mark Condy from the University of Alaska, because he kind of first plotted it in this format. He makes these spiral plots using different solar wind parameters. This is interplanetary magnetic field, BZ, which can give you a very good indicator of geomagnetic activity levels. And so if you see fluctuations in BZ, that means that you might have some favorable orientation of the magnetic field and you have some energy releasing into the magnetosphere. But if you look on this 27-day periodicity, you see that these things happen typically simultaneously with 27-day gaps between them. That's because there is a rotation of the sun, and that sun, the sun rotates with approximately 27-day period. And so if there's a certain region on the sun that's spitting out really, a really nice CME or a lot of plasma or something that's headed towards the Earth, 27 days later, if that active region is still there, it's a pretty good chance you're going to see more stuff coming your way in terms of geomagnetic activity. So it's interesting to look 27 days in the past and that helps us to predict what's coming. We can also look a few days or hours into the future using our satellites and models that we have, tools that are developed specifically for this. So there's this WSA NLIL model, which you can find a link to on NOAA's Space Weather Prediction Center site. And this is essentially showing plasma density. It's based on solar wind inputs from stereo and from our L1 assets, but also MHD modeling. So this is actually going through a Magneto Hydrodynamic model to get this data out. And this is showing what's going to happen in the future. I pulled this up this afternoon, and it looks like in about a day and a half or so, we're going to be right in the middle of this high density plasma plume that's coming off the sun, and we get this increase in plasma density at Earth, and so that might be a good time to look for enhanced geomagnetic activity. Probably not a Boulder, but in general, it's a nice tool to use. And then ACE is one of our satellites at the L1 point, the L1 Lagrange point. So it gives us a little bit of head start as to what kind of solar wind what kind of solar wind environment is coming our way. And so this satellite is sitting out at L1 and sending this real-time data back. And the most important thing we look at is probably the BZ component. So when you see a southward BZ that goes very strongly southward, or a fluctuating BZ with a lot of fluctuations, this is from the last 3 days, so nothing really stands out here. We've had sort of a quiet time, except for back on November 30th when we did have a slightly moderate enhanced activity. But if you look now to today, it looks like it's pretty low. But we also look at density, so you want to see sort of a low density, and you also want to see that speed start to increase as well. So you can look at this, we look at this when we're in the field, and this gives us it gives us a matter of hours head start to know what's coming our way. Solar wind environment. You can also go to this Geophysical Institute at the University of Alaska Fairbanks website. They use this ovation model from SWPC, from Space Weather Prediction Center website, to sort of project on a nicer map where the auroral oval is going to be in a day or 2 days from now. It's a prediction, and so it's not always correct, but they also give this probability of where the lower boundary of the aurora is, and occasionally it will dip down towards the Boulder region. So this is definitely something to go check if you think there's going to be enhanced activity, or you've heard about possibly a solar storm hitting the Earth's magnetosphere. You can also look at real-time KP. We look at this a lot as scientists. This is real-time disturbances in the magnetic field on the surface of the Earth, but it gives us a good indication of what the magnetic field is doing in that magnetosphere surrounding Earth. So the higher the KP, the more disturbed the magnetosphere is. You can see back on November 30th, we had this, somewhat moderate KP of 5. That's not really terribly high, so you still wouldn't have expected to be able to see anything in the Boulder region, but we did have some enhanced activity back on November 30th. The most real-time information that you can get, though, is from magnetometers. And so we have magnetometers sitting on GOES, which are 2 satellites in sun-synchronous orbits, in geosynchronous orbits around the Earth that have magnetometers on them. We can get both of those data in real time, and when you basically you see this large signal, which is the diurnal signal of the magnetometer, and you kind of want to ignore that wiggle. When you see these very sharp disturbances, such as this one coming down in the midnight region, that's when that indicates that there's energy being loaded into the magnetotail. And when you see that start to flip around and fly back upward, that means there's a substorm happening somewhere. It might not be, you might be in the wrong local time, it might not be in your region to see it, but this is something that if you're in a dark spot and you're maybe inside your house and you're waiting to see if there's going to be a substorm overhead, you can look at this in conjunction with your local magnetometer, so there is one in Boulder, and if you see the same sort of disturbance happening at the magnetometer on the ground in Boulder, then you really kind of want to rush outside and see if you can see the aurora happening as a result of that magnetic disturbance. So these are things that we use all the time, to sort of predict, and with even 10-minute lead time, we can sort of see if there's a substorm that's about to occur. So basically, if you want to see aurora, you have to go to Alaska in the winter or go to Norway in the winter. It doesn't happen at Boulder very often. Here's a plot showing the KP extent of the auroral oval, so with relation to KP levels, and you can see that it gets to Colorado around KP of 9. So when you have KP of 9, you're going to see aurora in Colorado. When you get to KP of 7, you might see it on the northern horizon. Anything lower than that, you probably won't see it here. But if you go to Alaska, and if you go to Alaska, especially in the wintertime, when you have lots of dark observing hours, it's very, very common to see aurora. You'll probably see aurora, and it's really a great thing to do. I highly recommend it. If you do want to stay in Colorado and just wait, you can. It does show up at these latitudes occasionally. You should hope for a new moon, or basically plan to observe when the moon is down and hasn't risen yet, or has already gone over the horizon, because that can wash out faint aurora. Of course, you want to get to a dark spot outside of town, and you want to look northeast, so find a spot where you can see the northern horizon, and you even want to look a little bit east. You have to stay up late, so a lot of these storms will happen past midnight. Warmth and food are extremely underrated. You want to dress up like a snowman and actually bring a lot of food, because you think, oh, it's not so cold out, but you stand out there for hours and it gets extremely cold. And then you also want to bring a real camera, because half the fun is trying to photograph it, not on your iPhone, but just on some kind of legitimate camera equipment. So if you want to learn any more about kind of what I've talked about tonight, on more of like a broader level or a broader scope, you should check out this book, The Aurora Watcher's Handbook by Neil Davis. I really enjoy it, and it's written by University of Alaska Fairbanks guy, and it's really entertaining. So thank you for your attention. Any questions? Yes.
So you're sitting in your observatory closet, and you've got one rocket that you get to use, and who makes the call to fire that rocket? That must be a pretty stressful decision.
Right, so the PI makes that call. The principal investigator of the mission, whatever rocket mission you're on, makes that call. That's been my advisor a couple of times, and so I've been the one sitting there right next to him, and we're trying to decide, and that's where the nail-biting part comes in, because you only get one shot. You know, it's not that much expense, and it's not that many years off your life, but you get one shot and that's it, so it's very stressful.
How does aurora show up in the radio spectrum, and how does it affect propagation?
Yeah, so it definitely affects propagation. You get if you get ionospheric disturbances, and that can be based on conductivity enhancements, and with auroral precipitation, of course, it can affect the conductivity of the ionosphere. So you get a lot of things like radio wave ducting, where you start to, maybe lose your signal or get signal in a funny place where you weren't expecting it. So things can get ducted through the ionosphere and then come down in a different location. Yes.
Why are the aurora so specific to midnight or past midnight? You made that really uniform.
Right. So if you think back to that movie that I showed, where you have the day side part of the magnetosphere facing the sun and the night side stretched tail that goes out into the anti-sunward direction. So that's where that magic reconnection happens, and generally is the thing that initiates the substorm.
Okay.
And so that happens on the anti-sunward direction, which is otherwise known as the night side.
Got it. Thank you.
Yes.
I was just wondering, have you seen Aurora in Boulder before? Does it happen often?
No, I've never. I've only been here a couple of years now, so someone who's lived here their whole life may have seen it. We've had several large storms. 2001, 91, March 91 was a big storm.
So I do hear people going north past Loveland, out where it's dark, and see,
Okay.
or going east towards Monty Grasslands.
And they've seen it regularly? Or?
No.
Yeah, sure, yeah.
Question?
Yes.
Aurora come in different colors. You mentioned which molecules or atoms correspond to which colors.
Yes. So essentially, it also depends on the density and the altitude profile of the density of atmospheric constituents, because you can get things like quenching, which will suppress certain emissions if you have too high of a density of a certain molecule. So there's a lot of kind of complicated chemistry that goes along with that. But basically, oxygen gives you red lines, oxygen gives you green lines, nitrogen gives you blue lines, and pink lines. That's the short answer. Yes?
Is it that the Coronal Aurora is typically around midnight, or is that not necessarily true?
Well, you know, just it depends on actually where you are. So the coronal aurora can change. It depends on where your latitude is at that time. So you have to be at the footprint of those field lines that the aurora is being produced on to see that coronal aurora.
So not necessarily a connection with the time of the day.
Well, I mean, a lot of those big substorms are concentrated in the midnight sector. They're also concentrated, you know, in that entire expanse around midnight. So it could be before, it could be after. Certainly. Yeah. Yes.
On that, I'm curious about this too. On that video that you showed of the green aurora, can you show like where someone could be standing to see a Coronal Aurora on that, or with that?
Yeah. Which video? The International Space Station video?
Yeah, that was the one.
Yeah. So basically, if you followed these rays down to where they hit the Earth, you'd want to be standing sort of straight underneath that and looking up. Yeah. So you know, hard to show on here, but basically follow that down. These rays are sort of mapping out these field lines in essence, and so if you stand sort of where those connect to the ground, then you're going to be looking up along those local field lines. Yeah. Yes?
On one of the maps, you showed some blue circles where you had the chances you're seeing an aurora dip. What were those blue circles on that map? I think that was the one.
Oh, the Aurora Source map?
Yeah.
That's a good question. Oh, those were pockets of observations.
Oh, okay.
So those are real-time tweets in which the system is getting information saying people are seeing aurora right now at those
The lowest altitude which occurred?
Sure. So that's going to be around 100 kilometers. It can be slightly lower. It can be 80 to 90 kilometers depending on higher energies. But we say that 100 or 110 is about the lower boundary of the world station.
I guess I flew through it over the Atlantic and it seemed like
Yeah. No, it does seem like it's really close, but it's not anywhere near an aircraft. Yeah. Although you can have other types of radiation, higher energy radiation associated with the same sort of magnetospheric processes that are actually coming down lower and affecting, that can actually impact the plane and the passengers.
They're not visible.
Not visible. Yes.
Why is it so columnar?
I'm sorry?
Why are the lights that are so columnar?
Oh, so those are following those magnetic field lines. So if you sort of go back to one of those schematics of the magnetosphere, all of these charged particles are essentially frozen into those field lines. And so this is, these are more widely spaced than you can see in those tall rays that we're looking at. But essentially, these are field lines coming in. You have field-aligned currents going across there, which means that there's electrons streaming down those. And so you're essentially mapping those magnetic field lines in terms of the photons that are emitted. That's where the electrons follow when they come in. Does that answer?
Yeah, that's brilliant.
Sorry, yes.
I was just wondering, you talked about how there's vortex-shaped aurora.
Yeah.
What would cause that?
Yeah, so that's when things start to get very active and dynamic. You have processes that are, you know, it's hard to see when you're looking at a 2D picture, but what's happening down in that tail is that when that magnetic reconnection happens and things are explosively contracting towards Earth, you can have things that are coming into or out of the plane and starting to twist those magnetic field lines, or we call them magnetic flux tubes. So down in here, we're just looking at 2D, but this can sort of start to tilt out of the plane, out of the board. And when that happens, you know, of course, this can affect the entire field line. You get twisting happening, and so if you imagine this blue line sort of twisting up, and then the aurora that happens down here will start to follow that, and what was a sheet could then start to turn into these curls and fold over on itself. In the back, way in the back.
How symmetric is the aurora between the northern and southern hemispheres?
Yeah, that's a good question. So there's been a lot of studies done on conjugacy of the aurora between hemispheres. There's data that's been shown that shows perfect conjugacy, and there's, of course, as with all these topics, there's data that shows that there isn't conjugacy. So it's probably something that happens at time, you know, often and then not at other times for whatever reason. Sort of an unknown question. One of the people that I did a lot of research with back when there was tons of funding, used to fly planes with the military. He'd get the military to fly planes in both the southern and northern hemisphere at the same time and take data and video footage and then sort of compare the two, and found that there was often a lot of conjugacy.
What is the best time in the southern hemisphere? Is it the same in the winter, for our winter, for them to see an aurora, or would it be?
No, so seasonal dependence is a little more tricky. The only reason winter is good here is because it's dark a lot, or it's dark at the higher latitudes, you know, all through the night and then into the dawn, and, you know, before that. So it's really based on the darkness. There is a little bit of a seasonal dependency between fall and spring, and seeing more sorts of aurora and more sorts of you get like a better connection between the Earth's magnetic field and the interplanetary magnetic field, and so there tends to be a statistical relationship between spring and fall, and seeing more enhanced geomagnetic activity at Earth. But other than that, it doesn't really matter. As long as it's dark, it can be daytime, and it can be winter or summer, and you'll see the aurora, as long as it's dark where you are. Yes, and yeah.
So is there any correlation between the color, the primary color of the aurora, and the solar activity level? Like, would more solar activity yield like more blues and purples?
Right. I mean, it just really depends on you know, where you are observing the aurora. So there's kind of always, if you have an auroral substorm, you often just have all the colors. Your eye is more sensitive to the green. And so if you're kind of closer to the source and you have the right equipment, you can see the entire spectrum of every, you know, single molecular chemistry thing that's happening with all the different colors. But if you're just looking with your eye, or you're looking from far away, you're really only going to be able to see the green. It's the color that your eye is most sensitive to. It just doesn't see the blues or the reds as well. But it's not connected to solar forcing, you know. Yes.
When curving is done in the aurora, is there any kind of measurable heat given off?
Yes, there is. There's definitely heating of the thermosphere, which we consider to be like the upper atmosphere that extends out into where we call space. So we do see a heating that occurs when you have precipitation coming down, and what that does is sort of inflates the entire thermosphere. You get higher densities at higher altitudes because everything sort of heats up and starts to expand upward. So there is a lot of heat with this energy input for sure. And that actually affects satellites as well, because they have to fly through that higher region. And if you get more density, it starts to affect their orbits.
What do you mean by density? Density of the aurora itself?
No, so it'll be density of the thermosphere, or the upper atmosphere. So when the aurora comes in, it'll dump that energy, and some of that does turn into heat, which then can expand the atmosphere.
So if I wanted to go see this and go to Fairbanks on a random basis, I spent a week there, what are my chances of seeing A, clear weather, B, an auroral event?
Right. It's actually the clear weather that's the difficult part. So I was there for a week-long conference a couple months ago, and there was aurora happening. We couldn't see it. It was just, everything was socked in, and you just couldn't see anything. So I don't know how to predict the weather. I know even less about that than space weather. So just have to cross your fingers. Yeah.